An example of a significance test. This is problem 29 on page 472 in your textbook. I hope you all know who John Wayne is. If you don't, every American should know who John Wayne is. Like a lot of other Americans, John Wayne died of cancer. But is there more to this story? In 1955, Wayne was in Utah shooting the film The Conqueror. Across the state line in Nevada, the United States military was testing atomic bombs. Radioactive fallout from those tests drifted across the film location. A total of 46 of the 220 people working on the film eventually died of cancer. Cancer experts estimate that one would expect only about 30 cancer deaths in a group this size. Is the death rate observed in the movie crew unusually high? And then does this prove that exposure to radiation may increase the risk of cancer? So when you go through a test like this, the very first thing that you're going to show or you want to figure out is your null hypotheses, which I talked about in a previous video. And you're going to take your null hypotheses, what we believe to be true. Okay, so what we are going to assume to be true. So when you look at the wording of the problem, it says that cancer experts estimate that one would expect about 30 cancer deaths in a group this size, so out of 220. So a lot of times you'll see this just referred to as P naught with a little, like H naught. So P naught would be 30 out of 220, which I reduced to 3 out of 22. So that's what we're assuming to be true. And then the wording of the question, is the death rate observed in the movie crew unusually high? So we want to see, that kind of gives us the direction. So you will have one of three things in this spot. Either P is greater than 3 over 22, P is less than 3 over 22, or P is not equal to 3 out of 22. So it really depends on the way the question is worded. I think on the M&M problem I did was a two-sided test. This is actually called a one-sided test. So once you decide what your hypotheses, and I recommend that you do symbols as well as words, and once you've decided that, of course, you have to check conditions. So my first one, I said it's reasonable, because it's not a random sample. Clearly, these are people on a movie crew, but it's reasonable to assume that the film crew is representative of all people in regards to developing cancer. So I don't really have any reason to believe that this group of people is any different than any other group. The second, I'm going to say, as long as they aren't related, it's reasonable to assume each crew member is independent of others. If you had people like a family that was on the set, then possibly if one person was more susceptible to cancer, maybe the others would be. So that would be that statement. And then I have to check NP. Now remember when we did confidence intervals, we used p hat. N times p hat is what we used, but we're not using p hat here. As a matter of fact, I haven't even looked at the p hat value yet because we are assuming this 3 over 22, we are assuming this to be true. So since we're assuming the p naught value to be true, that's the value that we have to use. So we have n times p, where p is 30 out of 220, or I could have reduced it 3 out of 22. And then n times 1 minus p naught would be 220 times 190 out of 220. And so both of those, I have 30 successes, 190 failures. So both of those clearly greater than or equal to 10. Again, it's very important that you use the p naught value. And then 220 is less than 10% of all Americans. So my conditions are met. Once I have determined that my conditions are met, I'm going to name my test. So I'm going to do a 1 proportion z-test because everything was met for that. I'm using an approximate normal model. My mean is 3 out of 22. My standard deviation, remember this is the square root of p times 1 minus p over n. So that's where and I'm using the p naught value because we believe that to be true. So now I'm set up for that. You don't have to use the formula to get your test statistic. Remember, your test statistic is your statistic minus your parameter divided by the standard error of the statistic. Now notice, this is the first time, this is the p-hat value, and this is the first time in the process we're even looking at p-hat. Up till there, we haven't even looked at that. So to do this on your calculator, if you go stat, test, and you find one proportion z-test, and now for p-naught, you can type it in as, you'll see that this is a decimal value. That's not what I typed in though. I typed in, if I clear this out, I typed in 3 divided by 22, and it just changed it to a decimal value. So now for X, that's the number of successes in our sample. We had 46 people die of cancer out of 220 people. And then you have to just tell it what kind of test. Was it a two-sided? Was it a left-tailed? This would be a one-sided left-tailed test. Or was it a greater than, which would be a right-tailed test? And that's what we are doing because this matches your hypotheses. So we did if you look back here, we did greater than because of the wording of the question. So then you come down and hit calculate, and you get these values, which I've cut and paste here, and I will talk about it from here. Let me close that and get, whoops, don't want to do that. Okay, so going on here, talking about what all these things mean. This is your test statistic, which is what you would get if you cranked this out in your calculator. This is your test statistic. Remember what that means? That means our value is over 3 standard deviations above the mean. So that's unusual. Our p-value, now be really careful. Do not tell me the p-value is 8.35. It's this e to the negative 4 tells you it's in scientific notation, so times 10 to the negative 4. So move the decimal point 4 places to the left. So you get this very small value. So I have a p-value of 0.0084. So what does that mean? A low p-value means we're going to have evidence to reject the null hypotheses. So here's my conclusion that I would state. And kind of a fill-in-the-blank type of thing. With such a low p-value, it's really important that you link your decision to the p-value. So this p-value is very low. With such a low p-value of 0.00084, we have strong evidence to reject the claim. So this is my decision to reject the null hypotheses, to reject the claim that the proportion of cancer deaths in the film crew is the same as the U.S. cancer percentage. The cancer fatality proportion is higher for the film crew. So when you reject the null hypotheses, which was this, the proportion of cancer, so I rejected the null hypotheses, which means I'm going to accept the alternative. So if you take the time to write out the words in your null hypotheses and your alternative, then you can go back and borrow those words when you're writing down your conclusion. But it's extremely important that you make a decision. So I'm rejecting the null hypotheses, I am accepting the alternative, and I am linking that to my low p-value. That's my evidence that I have to reject the null hypotheses. You absolutely have to have context. Okay, so you got to make sure that the context is in your conclusion. So what do we mean by a p-value? What does that mean? So a p-value is actually just a conditional probability. So the p-value means this. If the null hypothesis is true, as a matter of fact, I'm going to write it out that way. If the null hypothesis is true, then the probability of getting results as extreme or more than ours is p-value. Like a fill in the blank. So if the null hypothesis is true, now you wouldn't say if the null hypothesis is true, you're going to put the context there. So if the proportion of film crew deaths by cancer was really 30 over 220, that's like saying the null hypothesis is true, but I put the context. Then the probability of getting results as extreme or more than ours is, put the p-value there. That's what it means. It is a conditional probability. If the null hypothesis is true, the probability of getting results as extreme or more than ours is whatever the p-value is. But you always make sure that you add context. That is the whole process of a significance test that you would go through. Now there was a part B. Does this prove that exposure to radiation may increase the risk of cancer? That answer would be no. In order to do that, you'd have to do a controlled experiment, which would be unethical because you would have to say, okay, I'm going to randomly assign you to two groups, and one group is going to be exposed to radiation, and we'll see if you get cancer and die, and the other, so obviously you can't do that. So it cannot prove causation. The next problem I want to talk about is number 6 in your textbook. A survey investigating whether the proportion of today's high school seniors who own their own cars is higher than it was a decade ago finds a p-value of 0.017. Is it reasonable to conclude that more high schoolers have cars? Explain. So if this had been set up, now we don't have the numbers, we just have the p-value, but our null hypotheses probably would have said that our proportion was, well, we don't have the value, but the proportion was the same as it was a decade ago. So the proportion, and I'm just kind of doing this to give you an idea, the proportion was the same as a decade ago. I should have something about the cars in there. And our alternative probably was something about it's greater. The proportion in today is higher. Okay, they give us this p-value of 0.017, which is very low. So with a low p-value of 0.017, it is reasonable to conclude that more high schoolers have cars. If the proportion was the same as a decade ago, the probability of getting, it doesn't look like getting, results as extreme or more than ours, even though we don't know what the value is 0.017. Okay, that's a low p-value. How low is, when you get below 0.05, unless you are told something to measure it against, then you can pretty much consider that low. Low p-value means reject, so your null hypotheses. So that would be evidence for that. So there's a lot of confusion that can take place because we have a whole lot of p's in this topic, and I just kind of want to go over some of the things just to kind of make sure you realize what these stand for. We have P, which represents the true population proportion, which generally we don't know. We don't know what the true proportion is in the population. We have what we call P naught, which is a hypothesized population proportion. It's what we believe the population proportion is, what we're testing to see if it's that value. We call it P naught. It's the value. You don't have to call it P naught. It's the H naught value, where it might be P equals something, we don't know what. But a lot of times we refer to that as P naught, okay, that hypothesized value about the population proportion. We have P hat, which is our sample proportion. This does not get used until you calculate your test statistic, but we have that. And then we have the p-value, which don't confuse it with one of these proportions. A p-value is a conditional probability that we use to see if we have enough evidence to reject the null hypotheses. So you have to keep all those things straight because they are different. And when you look at the things on the calculator and what they tell you, they give you p. This is a p-value. This is not the population proportion or anything. That is the p-value. And they also give you the p-hat value. And they give you this value right here is our hypothesized value. So we have all that, but you just have to keep in mind what all those things are. And I know that that can be confusing, but we'll do lots of examples and you'll get used to it. So hopefully that helps a little bit with a significance test.